Alright, so I'm gonna be solving this problem today, which is restore the array. So I'll just skip the description, and I guess in simple ways, what we have to do is given a string, we want to partition it into valid partitions, where valid partition is when the string can be cast to an integer, and this integer would be between 1 and k. So up here, because this is 10,000, the only valid one is 1,000, because 1 on its own is not valid, 1 0 is not valid, 1 0 0 is not valid, because then you'll be left with these zeros, and 0 is not between 1 and k. Similarly here, there's 0 possible things, because we can't even reach the end. And then there's more complicated cases. So the way I'm going to be solving this is going to be using dynamic programming. And yeah, so I'll just go over what my framework for solving such problems is. So what is dynamic programming? In simple words, dynamic programming is when one state depends on another state and there's a recurrence relationship. And if we can remember the outputs of a state, then we can cut down computations a lot. So if you ask us, for example, compute a 10 Fibonacci number, if you could just remember the 8th and the 9th, and that's it, then it'll be just really easy to get the value of the 10th, rather than having to start again and again. And yeah, so if you had a person and we wanted to know how many descendants they had, if you could just get the number of children of like their children, and we already knew that number, then it would just be almost instant. So I guess the principle is memoization. So there's normally there's two ways to do it, either the top down or bottom up. So top down is recursive memoization. We can also use arrays here, so that's my bad. We can use arrays or hash maps. I wrote this a long time ago when I was more naive. And bottom up is where we start in a base case and we build up to our answer. So in Fibonacci, top down would be just like Tn equals to Tn plus Tn minus 1. So that's like the Fibonacci recursive relationship. And in here we just define the base case as when we get to n equals to 1 and n equals to 0, the values are 1. And we can solve it with that recursive relationship. Bottom up is when we start at 1 and 2. So not 1 and 2, 0 and 1. Index is 0 and 1 is going to be 1 and 1, and we build up to n. So in top down, we're going from top to the bottom, n to n all the way down to the base cases, and bottom up, we go from the base cases all the way to n. And this is the first time I'm using this software after a friend recommended it to me, and yeah, I'm not sure how this is. So define a recurrence relation. So we have to define this recurrence relation. We need to define the base cases. And my tips are hash maps are often easier to use. We don't have to worry about sizing the arrays. If bottom up isn't obvious, bottom up is often faster and also more efficient, just because we don't have to store the entire functions in memory. But yeah, top down's almost easy to implement, and we can actually build like the bottom up cases if we know the top down cases. Okay, let's just get right to it. So this problem here, we can define a recurrence relationship, and I'll define P as a position in S, or you can think of it as an index, and we'll define our base cases. So if you reach the end of an array, that means that's a valid partition. So if P reaches, if the current character that we are on is 0, or at the beginning if we encounter a 0, so if p is 0, then this is not going to be a valid partition, because we should never be starting a partition with 0, if that makes sense. So if we're starting any partition with 0, that's a bad partition. So these are our base cases. Next, we need to think about the actual recurrence. In our case, we're going to pass the current number. We're going to pass this, and we'll define a count as the number of valid partitions starting from this p. So what we're trying to do is the number of valid partitions starting from 0, for example, is going to be the number of partitions that can be created by every single number starting from this p plus the number of partitions that can be in here, the rest of the thing. I try to draw a picture, but it's not a great picture. So number of partitions starting from this character plus the number of partitions in the thing. So it's not even plus, it's basically, with ones and zeros, what we're doing is we create a partition here. If it's valid, we check if the next whole thing can be partitioned in a valid manner. And now we just want to check if car is less than or equal to k, and if, so the next thing cannot be 0, but we also need to account for it. What if we're at the end? So 1 and it just ends. So n of s equals to p plus 1, or so p plus 1 equals to 0 is not equal to 0 if the next thing is ending, or the next thing is not 0, then we need to explore everything after this point, which is just going to be at p plus 1. And then we're also going to grow from here, from this character. So I'm just going to go for I in range p plus 1 to the end. We're going to have to upgrade our current. So I'm just going to multiply by 10 and add. We're going to pass so I. We're going to check if current is less than or equal to k. If it is, then we do something with it. If it's not, we don't need to go any further. And now I also want to check if pretty much the same condition here, but instead of that, so the next thing is not 0, or the next thing is the end, plus 1. So the reason I didn't put this whole thing here is because, for example, if you had a case like 1 0 0 1, 1 0 is gonna be less than k, and I guess that's fine. But the next character is 0, so this, if I put it in the same line, it would just break, and we don't want that. We just want to actually try the next thing, so the next possible number if we append another character on. So starting from 0. So let's see if I made any mistakes here. The easiest way to check is just run the code, honestly. So it looks like that worked. And the question also says we want to modular the whole thing by 10 to the power 9 plus 7. Test some cases. It passed all of these cases. And we'll just submit it. Now, okay, I just realized, so I forgot to do the most important thing, the actual principle that differentiates dynamic programming from recurrence relationships. So this code is okay, it's valid, but it's not computationally efficient enough. So we actually need to remember things now. So what we're doing basically is that if we explored this, and then we explored this, and then we also explored this, when we get to the next character, if we already knew how many if there's any valid partitions in here, then we don't need to compute anything, we can just count them up. So in this case, in Python, all you can do is you can just cache a function. And what that means is that every time it encounters a p that this function has seen before, it'll just remember the output, the return value, and just return that rather than going through this entire loop again and doing all those recurrence relationships. So we'll cache the whole thing and submit again. And we go to TLE. Now another issue with this is that, if you can see, these are like very large numbers, and I'm assuming some of these numbers have become like this big. So in order to deal with that, we're gonna do the mod here because there's too many partitions here. Yeah, so that's a very, very big string. So the thing with modulo is you can't just modulo anywhere, but here we can, because it's just addition and multiplication. And hopefully this doesn't TLE. Cool, so this time it did not TLE. Yeah, so that was top-down dynamic programming. And yeah, I guess we could also convert this into bottom-up. How? That would be quite a complex undertaking. But in this case, I guess we know the size of our array now. It's gonna be, I'll just call it mem for memory. And counts are always 0 multiplied by length of s. And our base case is where p is the last one. Mem, the last thing is 1. And for, well, the second base case for C and S, and yeah, there you have it. That's the bottom-up approach, and you can see it's a lot faster. And you can also see how much harder it was for me, because I'm not used to thinking about it from a bottom-up perspective. But if you understand the top-down approach, the bottom-up normally isn't that difficult to achieve. Along the way, I got one wrong answer as well. I guess that's fine. I'm trying to see if I've done anything wrong, like something unnecessary. But yeah, I don't think, yeah, it is what it is. Cool. So I'm probably gonna speed up the middle bit that I took ages on, but hopefully you like that. Alright,